Let's take a look at a trig function and figure out where this is concave down and where this is concave up. Here we're looking at f of x equals tangent of x, and we're going to figure out where the water, like we said, runs down and where it holds water. Again, for step one, we're going to determine the second derivative. So we're going to take the first derivative first. Derivative of tangent is secant squared. Make sure you remember that rule. Now we're going to take the second derivative. So we will use the power rule here and as well as the chain rule to figure out the second derivative. So we're going to pull the 2 down. It's going to be 2 times secant, and then we're going to take the derivative of secant, which is secant times tangent. So again, this is the chain rule combined with the power rule. Then we will simplify that. Secant times secant is secant squared. So we are left with 2 secant squared times tangent for our second derivative. And now we want to figure out where it's concave up and concave down. So for step 2, we want to determine where the second derivative equals 0. Well, we really only have 2 factors that could be equal to 0. 2 won't matter, it never equals 0, and we have 2 secants and 1 tangent. So we'll just set 1 secant equal to 0 and the tangent equal to 0. So the question is, where does secant equal 0 on the unit circle, and where does tangent equal 0 on the unit circle? In other words, arctan of 0 and arcsecant of 0. Well, it turns out secant never equals 0 on the tangent line, and the reason for that is secant is defined as 1 over x. No matter what you plug in for x, you'll never get 0 back. Okay? Now, for tangent, it's y over x. Okay? So it's whenever the y value equals 0, which is at 0, pi, 2 pi, any multiple of pi. So I'm just going to write x equals n pi. Tangent will be equal to 0. So for right now, these are our critical values, and we have infinitely many for our second derivative, which is okay, because tangent x repeats itself, and we will include all values for concavity, so we might end up with a formula as our answer here, which is okay. It's what we want when we're talking about infinity and negative infinity. Remember, step 3, determine where the second derivative doesn't exist. Remember, that's also a point where the concavity might change, where it might be pointy or something. Like we looked at the last example, it went kind of like this. Now, however, in the last example, it didn't change concavity there, but it could. Let me actually show you what that might look like before we do this example. 1 second. So it could go like that, and then let's say it's pointy, and then it could possibly go something like this, okay? And it might have something pointy right there, and it would change concavity. It would go from decreasing tangent line to increasing. So at a cusp, for example, the concavity might change. So that's why we have to figure out where the derivative doesn't exist. So where does this not exist? Where it's whenever the denominator equals 0. If we convert these in terms of sine and cosine, so secant is equal to 1 over cosine, so secant squared is equal to 1 over cosine squared. Tangent is equal to sine over cosine. So we want to figure out where this second derivative doesn't exist. It's going to be where cosine equals 0. The squared won't matter, because if you take the square root, you still get 0 back. So where does cosine equal 0 in the unit circle? So arc cosine of 0 would be at 90, 270, it'd be 90, 450, and so on. So pi over 2, 3 pi over 2, 5 pi over 2. Now if you notice, all of these coefficients in the numerator are odd. So we replace these odd numbers with 2n plus 1, where n is a natural number. And so that will give us all the odd numbers, and then it's just pi over 2. Another way of writing that is n pi plus pi over 2. Either one of these will work. They will give you all odd coefficients, and this will be all the values on the y-axis. It will look like this. So for example, this angle, or this angle, or going all the way back around again. So all of those different multiples of pi over 2. So these are some more critical values we have to take into account when doing our second derivative chart. Next, we're going to determine our intervals. Now here's the thing. we're going from negative infinity to infinity, but if we just do one complete revolution of the circle, we can get a good idea of where our critical values are and come up with a general formula for, our intervals of concavity. So we're going to go from 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, 3 pi over 2 to 2 pi. Just to refresh your memory, we got those values from, first of all, figuring out where tangent was equal to 0, right, from where we set it equal to 0. And we got multiples of pi in pi. And then, of course, we just now figured out multiples of pi over 2 where cosine equals 0. So there's our intervals, at least partially. We will use those to write a general formula for concavity for tangent. So our first interval is 0 to pi over 2, second one's pi over 2 to pi, third is pi to 3 pi over 2, finally we have 3 pi over 2 to 2 pi. First test value would be an angle between 0 and pi over 2. We're going to do pi over 4. Just to let you know, it would look like this angle right here. Next, from pi over 2 to pi would be 3 pi over 4, or 135, which is between 90 and 180. Next, we have pi to 3 pi over 2, or 180 to 270. And between that would be 225, or 5 pi over 4. Then we have 3 pi over 2 to 2 pi, and between those two would be 7 pi over 4, or 315 degrees. So we're going to plug those into the second derivative and evaluate them. Now secant of pi over 4 is square root of 2. If you square it, you get 2 back. So it's 2 times 2, which is 4. And then tangent of pi over 4 is 1. So it looks like I might have got that value wrong. Let me double check my work real quick. Okay, yeah, so this should be 4 because secant of pi over 4 is square root of 2. If you square it, you get 2 back. 2 times 2 is 4, and then tangent of pi over 4 is 1, so you get 4. Same thing for these down here. Secant of 3 pi over 4 is negative radical 2. When you square it, you get positive 2. 2 times 2 is 4, but then tangent of 3 pi over 4 is negative 1, so you get negative 4. Going back to 5 pi over 4, secant is negative square root of 2. You square it and you get 2 times 2, which is 4, and tangent of 5 pi over 4 is positive 1, so you get 4 again. 7 pi over 4, secant of 7 pi over 4 is square root of 2, positive, square it and you get 2. 2 times 2 is 4, but tangent of 7 pi over 4 is negative 1, so you get negative 1 times 4, which is negative 4. So what does this tell us? It tells us from 0 to pi over 2, since we got a positive number back, it's going to be concave up from 0 to pi over 2. From pi over 2 to pi, we got negative, it's going to be concave down. From pi to 3 pi over 2, we got positive, so in our sine column, we put positive. In our concavity column, we put it concave up. And finally, from 3 pi over 2 to 2 pi, we got negative 4. That's a negative sign, so we know it's going to be concave down. So what does this mean in terms of intervals and in terms of infinity? Now what we need to do is come up with a general formula for when this function is concave down. Well, let's look at these two intervals right here. We have pi over 2 to pi and 3 pi over 2 to 2 pi. Both of these are going to be concave down. We know it's going to repeat itself based on what we got up here with these critical values. We just need to figure out a general formula for concave down. Well, if you look at the numerators here, these are odd numerators for when it's concave down. So the first one would be 1 pi over 2. And then we go to 3 pi over 2. You can imagine the next one's going to be 5 pi over 2. So it's going to be of the form of an odd number. Okay, next, it goes to, for the first one, pi. And that coefficient is going to be 1. And then it goes to 2 pi. So you can imagine that the next one's going to be 3 pi, 4 pi. So those are just going to be n, right? So n will represent the coefficient of the second part of this interval where it's concave down. The question is, how do we do the first one? We know it's going to be odd. Since the first one is 1, we can't do 2n plus 1 because that would give us 3. So we're going to do 2n minus 1. That would work when we plugged in 2 here because 2 times 2 is 4, minus 1 is 3. So it's going to be concave down from 2n minus 1 pi over 2 to n pi. Again, that will give us any interval where it's concave down. How about where it's concave up? Well, it goes from 0 to pi over 2, then from pi to 3 pi over 2. Both of these intervals are going to be concave up. So you can see that the second part of this interval is going to be like the first part of these intervals. And in the same way, the first part of the interval for concave up starts with 0 pi, then it's going to be 1 pi. Okay, you can imagine the next interval down here is going to be 2 pi to 5 pi over 2. So we just need to come up with a formula for concave up. This one will be concave up from on the intervals n pi to 2n plus 1 pi over 2. The reason this will work, let's say we plug in 0 for n, we'd get 0, comma 1 pi over 2, which was our first interval for concave up. If we plugged in 1 for n, we get pi, comma 2n plus 1, which would give us 3 pi over 2, and so on and so forth. So you need these formulas in order to determine where tangent's going to be concave down and concave up for any interval, not just from 0 to 2 pi. Now that we've done all that work, let's take a look at the graph. Okay, we're going to start from negative infinity. We're going to go ahead and trace out. We can see that it starts out concave down because the tangent line is decreasing and water falls off. But we can see right there at negative pi, it's going to start doing what? It's going to start being concave up. The tangent line will increase, the water will hold water, and then it kind of jumps because it's undefined there. It goes back to concave down, then there at 0 pi, it changes to concave up, then it jumps again at, looks like, pi over 2, goes to concave down again, changes to concave up at pi, and repeats. Now I want you to notice something. There are asymptotes here on this graph. So for example, right here, from at pi over 2, there is no point specifically where it changes concavity, it jumps. Talked about inflection point, which is where it changes concavity. There is no inflection point there. So just because you have a second derivative graph and you have change in concavity doesn't necessarily mean there's going to be an inflection point there. It could just be an asymptote or something else. But anyways, that's the graph. It reflects what we found here on this chart. And just remember that, you can come up with formulas for inflection points for trig functions, especially for these functions that repeat themselves. So that's it for intervals of concavity. In this case, we were looking at tangent of x. If you have any other questions about this example, let me know.